Welcome to breadboarding. In the previous video we managed to get our CGA video controller installed here and connected up to the rest of the breadboard PC, and we managed to get a basic colour test pattern coming out. What that indicated is we've managed to set up the cathode ray tube controller chip here and the video digital analog converter here and connected it up okay to the 15-pin VGA connector here. And what we were doing there is basically just feeding the digital analog converter with some of the address lines coming out of the cathode ray tube controller here, which just gave us the pattern here. What we're going to be doing in this video is we've got the character generator ROM or EEPROM down the bottom here, and there's also a shift register here, and what we're going to be doing is configuring these to output the character sets, the fonts and character sets, using similar address lines coming out of that, and we should get some sort of output, something like this. This is a dump of the 256 characters which are in the fonts, and it just repeats down the screen. This is video 13 of the Breadboard ATF1504 PC version 2, and this is part of the version 2 high-level plan. We've already completed the first third there, which was the Nanocomp AT88, a basic AT88 based computer with an LED display and keypad and built-in monitor. Once we've finished the CGA video controller text mode, we'll be adding the floppy disk controller so we can boot MS-DOS. And then later on in the series, we'll be adding an IDE disk controller, configuring the IDE BIOS, adding some more graphics modes to the CGA video card, add a mouse, and then running early versions of Windows. So in the previous video, we managed to get the cathode ray tube controller running. So this is a Motorola 6845 compatible chip. In fact, it's a Hitachi chip, which is a little bit more capable of the original Motorola one. We got our I/O port decoding, the 25 MHz dot clock, a complex PLD, the ATF1508, with just really the clock part of that we're using at the moment. We also got the video digital analog converter updated by the test program so that we could produce the text output pattern. So in this video, what we're going to be doing is adding the character generator ROM. Now, the character generator ROM is fed by the CRTC row address line. So normally that would be RA0 to RA2 for providing 8 lines. However, because the default CGA card was 200 lines and we want to output 400 lines for VGA compatibility, then what we're going to do is to skip the RA0 and we're just going to be using the RA1, 2 and 3. So this will actually tell the character generator on which row of each character we want to output. And then the address lines A3 to A10, that will actually just provide an 8-bit value telling us which character code we want. And in fact, to start with, we haven't got any video RAM, so we're just going to plug in the outputs from the CRTC address lines, and that'll actually give us that repeating pattern. What that then does is outputs the raster pattern for each character row, and we then feed that into this shift register. The shift register is latched by the attribute shift register latch, and it's also controlled by the dot clock. So what it does is loads the 8 bits of the character into the shift register, and then on each dot clock it cycles those around. Then the output bit from here is then going to be fed into our digital analog converter. We can either hook it up to the blue input line, or we could reconfigure this to only have black and white values for the video palette. And then that should produce our test pattern that we had on the previous slide. So let's take a look at the KiCad schematic to look at what we need to connect. So this is a CGA video controller. You can see the ATF1508 Complex PLD here. A lot of the chips have been replaced by this. Down the bottom here we have a 28C64, which is an 8K EEPROM, and this will allow us to include 2 CGA fonts and 1 VGA font should we need it. And in fact, some of the address lines here can switch between the CGA thin fonts and the CGA wide fonts, and also to be able to switch between the CGA fonts and the VGA ones. And the reason for this is we might actually want to output a more VGA compatible display if we want to get better looking output from this. So the address lines coming in here, so the CH0 through to CH7, we're actually going to be feeding those into the CRTC memory address lines up here like we did previously with the video DAC. And then the dot data coming out of here. So this is the raster line for each of the characters, depending on which row address coming out of the CRTC. And this actually then goes into the parallel input of our shift register here. The attribute shift register latch, this will actually clock the bits values into here. And then the dot clock here will then output the bits through QH, which goes into the serial dots input of the complex PLD. And all we'll be doing is we're taking this output here and we'll be plugging it into the video DAC up here. We can either just plug it into one of these lines here, really, probably just P0, and switch between 0 and 1 to show us black and white. That's what we're going to be doing. We also just need to have a quick look at what fonts we're going to be using. So in the introduction video to the CGA card, I did cover the different fonts. So the CGA default was 640 pixels across by 200 lines, and the default font actually had vertical strokes in the characters were 2 pixels wide, and each character was based on 8 by 8 pixels. There was also a thin font as well, where the verticals were 1 pixel wide, but still basically 8 by 8 pixels. So that was the 2 CGA fonts. So if you compare, this is the wide one, this is the thin one. I think the wide one was more for use on TV type displays, whereas the thin one could be used on higher resolution dedicated monitors. Then the monochrome display adapter used a higher resolution at 640 across but 350 lines. That meant that each of the characters was made up of 14 pixels vertically, and it also included 9 pixels across, so there was actually a gap at the end of the line. And for certain of these graphics characters, there is some dedicated logic that would take the last pixel for the character here and would also bleed that onto the 9th pixel. So there weren't any gaps between the graphics characters. And then finally, the VGA character set. The VGA resolution was actually 640 pixels across by 400 lines. Actually, normally the VGA text mode would be running at 70 Hz, which was 400 lines, not 480. And this could also do 720 pixels across if we wanted to have 9 pixel wide characters, but we're just going to be using the 8 wide ones for now. And these characters were 8 by 16 pixels. So again, you can see that these characters look a bit cleaner than when we compare to the default CGA ones. So we're going to program both the CGA thin and wide characters and also the VGA, and we can actually switch between those. We can actually change some of the address links on the character generator EEPROM there. We can output the different fonts. So I've covered this previously. There is a great site here, the int10.h.org is a good site for all this sort of stuff. Interrupt 10 is the BIOS interrupt for the video subsystem. So the CGA fonts are 8 bits wide by 8 high, VGA 8 bits wide by 16 high, and by default we'll probably use the thick characters, but I think that the thin characters probably look better on the video capture hardware that we're using. And the utility fontraption, which is available at this URL, and the zip file here includes all of the fonts I'll be showing you, can actually show you this is the wide characters here, you see 2 pixels wide, and then when you look at the thin ones, you can see they're only 1 pixel wide. So I'm just going to take a look at fontraption, or frapped as it's known, and we're going to run this under DOSBox. And what that will allow us to do is to identify what are the font files that we actually want to burn into the character generator EEPROM. So let's go to DOSBox. So the first thing we need to do is to mount C drive. So I've got all the files on my local C drive under DOS. So if we go to C, if we look at what we've got there, we just need to go into fonts. Now I've got a number of the font files already in this folder here. We can, if we want to, drill down and have a look at all of the fonts in there, but there's a lot of different fonts. I've just picked out the CGA ones, the VGA and the MDA ones that we need for this. We're just going to run up frapped. So by default it has the default VGA fonts, but if we want to load a font file, I'm just going to select the default CGA one here. That CGA F08 means that it's made up of 8 lines. Then if we go to the second font here, I can then load the thin font. So you can see here CGA thin. And so you can see there we've got the 1 pixel wide, the vertical strokes there. And when we look at the default one, we've got 2. And if we want to, we can then navigate around. So you can see that the 000 is in fact a blank character. And if we have a look at this graphics character here, you can see that 219 is the 8x8 cell. And if things were running with a 9-dot cell, then this would in fact be widened. And you can see there's a F8 here. Over on the right hand side here, if you press the F8 key, it will switch between 8 pixel wide character cells and 9 pixel wide character cells. So the video hardware would actually expand the 8th pixel to fill the 9th pixel if we were running in 9 pixel mode. But we're going to run things in 8 pixel mode because there's no real benefit in running with 9 pixel. So this is the 2 CGA fonts we're going to be using. If we then also have a look at the VGA font, you see we've got VGA 8 F16. See that these characters are then made up of thicker characters and also up to 16 lines, and this gives enough space for the cursor to comfortably go underneath here. So what we're going to do now is to program the character generator EEPROM. So we're going to load these 3 fonts in. So the wide one's going to go in at the bottom, then we're going to put the thin one, which are these are both 2K each, and then we'll put the VGA one in the top 4K. Okay, so now let's program the character generator EEPROM. So just go into the EEPROM programmer software. Okay, so I just need to select the chip type. I do need to make sure that this is the AT28C64B, otherwise I might get errors. If you don't have the B on the end there, you'll end up with problems. So just try reading this. Yep. That is blank, and you can see it goes down to 1FFFF, which is 8K. So we need to load in first of all the default CGA font. So this will be CGA F08, that's the thick font. Now we don't need to worry about clearing the buffer because there's nothing here, but we will need to disable this clear buffer and put an offset on here for the subsequent fonts. Okay, so we can now see this is going from 0, should go down to 7FF, and then 80 is the offset we need for the next one. So now we need to disable the clearing the buffer. The offset now needs to be 800. So that is 2K in hexadecimal. And now we need to choose the thin font. You can see that's now loaded in there. That should go all the way down to 1000. Okay, so now we can load in the VGA font. Again, we don't want to clear the buffer. You want this to be 1000, and then VGA 8 bits wide, 16 lines. And we can see that now goes down to the bottom of the EEPROM. Okay, so I'm just going to program that now. So I'm just going to put that back into the board, and then we're going to start wiring things up. Okay, so here's the board. I'm just going to take out our little power meter out of there so we've got a bit more space. So we're going to be wiring up the power lines and the various tying things to ground and to 5 volts. Going to wire in this one as well. We're going to be wiring in 8 of the outputs from the CRTC over here. Going to come over to the various character select lines here. We're also going to need to take 3 of the row address lines there and feed those in over here as well. And then the outputs from the dot data here are going to be going into the parallel inputs over here. So I'm just going to go and wire all that up, and then when we come back we should be ready to switch this on, and then we'll check to see whether the serial out here, if we feed that into one of the inputs over here, we should then be able to get our character generator data appearing on screen. Okay, so going to hook up the power first. Right enable's tied to 5 volts as well. Character generator output enable needs to be tied to ground for the moment. When we introduce graphics mode, so we need to turn the character generator output here sometimes when we're in the high-res graphics mode, because the high-res graphics gets the dot data from here. Selects the wide characters, hardwire character generator output enable, and chip select is also hardwired to ground to enable. CGA selected to CGA, ground, VCC, ATSR latch, serial, lock inhibit and ground all need to go to ground there as well. Serial in ground, clock inhibit, also ground, and ground connected to ground. Yes, that's all of the tied to ground and 5 volts, which has been done. Now I need to hook up the dot data. So dot data 0, 1 and 2 is going to go to 0, 1 and 2 over here. And then we'll do 4 through to 7, going to go through 4 through to 7. Number 3 is on its own round here, that goes round to here. A goes to dot data 0, B goes to dot data 1, C goes to dot data 2, D goes to dot data 3, E goes to dot data 4, F goes to dot data 5, G goes to dot data 6, and H goes to dot data 7. Now we need to hook up the attribute shift register latch, which is pin 44. The clear shift register is pin 45 and goes to there. And then we have a second dot clock, so there's a dot clock at the top there, but that's also repeated down here, and that goes to clock. So we just need to wire those 3 up. So this is the dot clock. This is the clear. Then this is the attribute shift register latch. Goes to SL. Now the output here, which is QN here, that is going to go to S dots in here when we're actually doing all the attributes. But for the moment, we're just going to wire in the fly lead here. And this is going to go over to the input to the video DAC. We're just going to take the leads off of that. Going to connect these to ground. Take out that additional connection there. P1 to P4 is now connected to ground. And the output from our character generator is going to select P0 between 1 and 0. So at the moment that should produce black and blue, and we can obviously change that to make the blue or palette 1 to be white. That's connected there. The only thing we need to do now is to hook up the various address lines. So I need to connect RA1, 2 and 3 to these pins here, and that's coming from RA1, 2 and 3 up here. RA0 is not connected at the moment. So RA1, 2 and 3, RA1 being orange. So that's RA1, 2 and 3 wired in. And then this is going to take the address lines just feeding into the character select, and that is going to come from the character latch when we've wired up the rest of the logic. But for the moment, we're just going to wire this in to the MA0 to MA7. Okay, so this is all wired up now. Don't need to change anything on the Complex PLD. It should all be working from last time. We're still plugged into the VGA capture card there. So I'm just going to load up the software and we'll have a look and see if we can get some video output. Okay, so I'm just going to download our test software that we used last time. So I'm just putting the nanocomp into load mode. That's loaded. If we just switch over to the VGA capture, I'm just going to run the program. That looks like we've got the output that we'd expect. Now at the moment, I've only plugged the S-dots output from the shift register going directly into the P0 input of the video DAC. Now at the moment, that means it's choosing the palette number 1 out of the range that we've got there, which means it's blue. What I can do is just change the software so that we make palette number 1 to be white. This is the test program we used last time. And all we need to do here, you see that by default, the palette entry number 1 is blue. So all we need to do is to comment out that line there, comment out this line, save that, assemble it, and if we just go into load again, send the updated file, then we'll switch on to the VGA capture and run this, and you can see now that is now in white. So that's what we would expect. That appears to be working okay. Now there were a few problems I had along the way. What I discovered is that when I first ran this, the output wasn't looking quite right. And in fact, what I found were there are a few minor issues. The main one was that the attribute latch in the original clock PLD, the attribute latch had an inverted signal, and also the character latch. That means that it would be active low. And when I looked at the logic analyzer output, so this was the logic analyzer output. What I did is I fixed on a particular character. So there is a character in the character set that has alternating 1s and 0s. So you can see here that the character B1 has this pattern of alternating 1s and 0s. And if we go to the ROM, you can in fact see that when you work out what B1 times 8, that actually is 588. And you can see here that we've got 55AA, 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 55AA. So 55 and AA are the alternating 1s and 0 patterns. What you can see here is that we've got the AA and 55, and because we've got 2 lines per set of pixels, you can see that the horizontal sync down here, we have 2 horizontal sync intervals as AA, then it goes to 55. Then if we have a look at the dot clock, we can see that that is sort of alternating at 25 megahertz. And we can see that the attribute latch is going high and then low, but the S dots coming out here, we would expect to be alternating at half the dot clock frequency, and that was not what we were seeing. And in fact, if I have a look at one of the screenshots from that time, so in fact the screenshot had this sort of pattern on it, and what I would have expected is more of a sort of alternating 1s and 0s, alternate lines. And in fact, this is what I was expecting it to be. You can see that it's kind of like difficult to see because it uses JPEG, but you can sort of see that it is alternating 1s and 0s on there when it was working. And what I realized the problem was is the polarity of the attribute latch there was incorrect. It should have been going negative. and that probably explained the reason why we weren't seeing the values that we were expecting. So if we look at the other logic analyzer, you can see now that the attribute latch is now active going low, and in fact when we have these alternating periods, you can now see that the output, the S dot, is in fact alternating between ones and zeros at sort of half the frequency of the dot clock, which is what we'd expect. And that was then shown on this pattern here, shows that alternating ones and zeros. Not very easy to see, but when looking up close to the display, it looked fine. So all I had to do is to reprogram the Complex PLD with these inverted values in there. And I also found that I needed to hard code the video enable also to be 1, because the clear shift register was dependent on the video enable. So by doing that, it also means that that output should also be correct as well. That looks like it's all working. The character generator ROM's been programmed, and we've got it to send the output to the shift register, and that is now also configured to show the test pattern on the screen. We managed to change the color palette just to show black and white for the ones and zeros going in there. So I'm going to break the video there. In the next video, what we'll be doing is looking at adding the color and attribute control. So I'll be doing some more work on configuring the Complex PLD to be able to send colors and blinking and flash, that type of thing, onto the video. So if you don't want to miss out on future videos, please hit subscribe. And if you could hit like as well, it just helps to make the videos available for more people. Thanks for watching.